Okay, so we went over this. I remember we drew the equilibrium expression for each of those. Okay, so we're familiar with heterogeneous equilibrium, and that basically means what again? Different phases. That's right. So when we're working with different phases, gases and aqueous solutions are going to be counted in the equilibrium expression, but solids and pure liquids aren't. Okay. Gases, let me write it down. So we'll say, there we go. Say gases and aqueous solutions are included in equilibrium expressions. But pure solids and liquids are not. So, in other words, those guys are involved in the reaction, but they're not going to be affecting the equilibrium. So the equilibrium is only going to be affected by those things that can make those minor changes. Okay. So the equilibrium position is going to be independent of the amount of solid or liquid that's present. And that's as long as there's at least some present in our reaction. Now, if there's none present, then of course that's, you're not going to have to be able to do anything. Okay. Okay. Come on. Oops. Yeah, I'm having a lot of trouble with my computer today. It has a mind of its own. Okay. So that basically means, again, the quotient and the equilibrium isn't going to be affected by it as well. So long as there's some of it present. Okay, so let's talk about Le Chatelier's principle. So Le Chatelier's principle is basically when we're putting stress on the equilibrium system. So again, when we think about equilibrium, this here is kind of like signifying equilibrium. So these molecules are going up into the vapor, right? And then at the same time, you have other molecules that are going to be going down, right? If I could draw. So we're going to have other molecules that are going to be going down like this, right? And so the rate of this stuff going up is going to be the same as the stuff that's going down, right? The rate is, but the amount doesn't necessarily have to be the same. Okay. So now, once it's in equilibrium, once it satisfies its range in equilibrium so that those rates are exactly the same, right? The stuff that's going up matches the rate of the stuff that's going down. Okay. Now we could put stress on a system. So let's say, for instance, we have A plus B is in equilibrium with AB. Okay. So The Shortlist principle basically says if I put stress on the system, let's say if I start taking out, I start removing A from our system. I'm sorry, removing AB from our system. So if I do that, now it's an equilibrium. The system is a closed system, and all of a sudden I'm removing my product, what I'm making, right? That's going to shift the reaction. In this direction, because we're taking this away, so we have to start making more of it to replace the amount that we've taken away. Okay, and it's going to do that until it reaches equilibrium again. Okay, but if I'm constantly taking this out, it's going to be constantly driving that reaction, as long as we have reactants available. Okay, can you guys see that when I point up here about a cell?
Yes, we can see it.
Yeah.
Good. Good. It's good to know. Okay. Sounds familiar? Yeah. Man, it's funny how this works, right? You hear it over and over again. Okay. So if I increase, say we increase A, right? So I just start adding a whole bunch of A in there. As long as I have B, it's going to drive this reaction again towards the products. Okay, long as there's B present, it's just going to be pushing it that much further towards the products. Let's say somebody gave me a starter batch of AB, right? And so now I'm increasing AB. Let me erase this. What's going to happen now? So I just start dumping a whole bunch of AB, into our vat. Toward the reactants. Yep, so it's going to be going in this direction, right? Okay, so that's called the Shortlist shift. Okay, so that's the Shortlist principle. Yeah, it's a dance, Okay, so at equilibrium, and that's based upon the fact that at equilibrium, I guess maybe I should erase this so you guys can see stuff. You guys want to see stuff, right? Okay, so at equilibrium, Q and K are going to be the same, right? So as soon as we start screwing up with it, then we're shifting back to Q. And so that means that we have to try to get back to K. Okay, so the key is that once you're in equilibrium, you're always going to try to get back to equilibrium, right? So if you do something to disrupt the system, you want to try to get back to equilibrium. Okay, so if you add products or you remove products, it's going to shift the reactants. Does that make sense? Or if I add reactants or remove reactants, that's also going to cause a shift. Okay. So if we're at chemical equilibrium and we disrupt by either adding a reactant or a product, it's going to be shifting in the opposite direction, right? So if we're adding more of the reactant, we're going to be shifting towards the product. So we're going to push the equilibrium towards the product. If we add more product, then we're going to be shifting towards the reactant. If we remove reactant, right, we're taking out the reactant, it's going to move towards the reactant. If we remove product, we're going to be moving towards the product. Okay. So now let's say we're talking about gases. It's all gas, in a closed container. That's going to be important. Okay. So if we're talking about, let's say, gas that's going into a liquid, right, to liquid form. So we put more and more gas in there in our system. What is that going to do? Okay, so let's say we have this. Let's do water, right? Let's do we'll just say, just do your general. Say A liquid, L. Okay, and gay, A gas. Okay, so A liquid, A gas. Okay, so if I decide to put more A gas into our system, what's going to happen? It's going to go towards the liquid. Okay. Now, if I go have more liquid, then what's going to happen? It's going to go towards the gas. Now, what if I put gas B in here? Why? Okay. So, but even though the gas B isn't part of the reaction, why is it going to push it back into the liquid phase? That's right. Because it's taking up more space, it's going to drive the equilibrium. Okay? Okay. But that's only in the cases of gases, right? Yeah. Does that make sense? A little bit. Okay. Okay, so don't worry about it. We'll have examples here in a second. Okay. So if we have a change in temperature, what does increasing the temperature do? Okay, it is going to mess with pressure if it's in the case of gases. Yeah. It can also mess with phases. That's true. So that's two things that it's going to, how it can change the system. And then what else? What else can it do? What does temperature, increasing the temperature do in general? What was that? It changes the rate. Okay. So if it changes the rate, that means that now your equilibrium constant is also going to change, right? Because the rates are going to change. Okay. So let's see how that's going to affect us. Let me clear this out so you guys can actually see something. Can you guys hear me? Am I talking loud enough, Marisol?
Yeah.
Yeah, I can hear you.
And Abel. I didn't forget about you, Abel, but she's on top of the screen. The first one that says, so I always ask her. So. Okay, so so we know that changing the temperature is going to change our equilibrium constant, which because we know that that's going to change each of the rates going back and forth, and at equilibrium, those rates have to be exactly the same. Okay. So if the forward reaction is exothermic, what does exothermic mean again? It releases energy, or releases heat. So then K decreases as temperature increases. So that means that the equilibrium constant is going to get lower as the temperature rises. Okay. Yeah, sort of. In terms of only opposite direction, only thing with PV equals nRT, pressure increases, temperature increases. That. Okay, so in the case of a forward reaction is endothermic, and that means basically energy has to be put into the system. Then K is going to increase as temperature increases, right? So they're going to be directly proportional. Indirectly, when it's exothermic, and directly, yep. Okay. Now, catalysts. What do you guys think is going to happen with catalysts? No, when to our equilibrium. Will it increase K? So it wouldn't do anything. That's correct. It wouldn't do anything. There wouldn't be an effect, right? Because all a catalyst does is just kind of speeds up the rate. But then if you're speeding up the rate, then your other rate has to match it anyway. So, yeah. So you're not going to have, ultimately, you're not going to have an effect on your equilibrium. You just basically reach the equilibrium faster. Yeah, yeah, it's like a shortcut. Exactly. You're taking a shortcut home. Yeah. Okay. Okay, so let's test out the Shortlist principle. Okay, so here's our chemical equation. Carbon monoxide plus, that would be iron 4. No, that isn't iron 4. That is what? Iron 2. I can't do math today. So that's 2, that's 8. That does not add up correctly. 4. So that does not add up at all. So 3 times what equals 8? So whatever this compound is, I have to see what I did. This is iron 2, but I don't know what the hell this is. So it can't be 2. So it has to be either peroxide or no, superoxide. So it has to be iron superoxide for that to work out. All right. No, that wouldn't work out either. Anyway, let's say we have this chemical compound. I have to figure it out. So, and we add carbon monoxide gas. What's going to happen? So in other words, we have this already in equilibrium, and now we're adding more carbon monoxide. Okay, so it's going to shift to the from left to right, so shift to the right. Okay, so in this case, we're removing carbon dioxide. So which way are we shifting? We'll make it. So we're shifting to the right. Yeah, so we're shifting right. Okay. And we'll say if it's shifting left, we'll make it pink. So since I know you can't tell what it is, so if it goes this way, okay, we'll use pink. Okay, so if I add more, the addition of iron oxide to the system, we're adding more. Now, look at the state. What is the rule about the state? What was that? Nothing. Nothing's going to happen unless we use up all of it. Then that's different, right? As long as there's some there, nothing's going to happen. So no effect. So we'll say we'll use yellow for NA. NA or any, no effect. Okay. And then the addition of carbon dioxide. So we're pushing it to the left. Okay, you guys get that? Able?
Yep.
Yep. Okay, let's see. We got more. What about here? Come on. Okay, so if we increase the pressure of the hydrogen gas in this equation, so increasing the pressure will go to the right. Okay, so we'll say green. Okay, so if we increase the pressure of the hydrogen iodide, hydrogen monoiodide, so to the left. That's correct. If we increase the pressure of iodide, decrease the pressure of iodide to the left. And if we decrease the pressure of hydrogen monoiodide, was it to the right? That's correct. Okay. Okay, now we're gonna make it a little more challenging. But get stiff sitting down all day. Okay, so here's our chemical equation. First off, is it endothermic or exothermic, Abel? The first one.
Let's see. Exothermic?
Are you sure?
No. It's endothermic. And the bottom one is exo.
That is correct, right? The way that we know is that if it's a positive value, we're adding it to the system. The negative value is being released. Okay. Okay, so heat is added to the system. Now we're adding more heat. What is that going to do? How's that going to affect the reaction? Are you sure? Think of it as a product, right? Or a product or a reactant. Heat is heat a product or a reactant? If it's endothermic, an endothermic reaction, it is a reactant. So if we have more of this reactant, what is that going to do? What is that going to do? It's going to go to the right. Right? So if we cool the system, in this case, now we're removing heat from our system. It's going to go to the left, right? Okay, so here, if we're heating up the system, it's going to go towards my reactant. So it's going to go to the left. And then if we cool down the system, it's going to go to the right. Okay, questions? Concerns? $2 million? Yeah, me too. As soon as you guys give it to me, I'm good to go. Okay. Okay. So, that's right. So in the case of when we're looking at the total pressure, right? So we have gases, and we're going to be looking at the total pressure, okay? So equilibrium is going to shift as a result of the total pressure by the addition of non-reacting gases. So if we increase the total pressure of the system, then, oh yeah, okay, so if we're increasing the total pressure of the system, then it's going to be based upon how many you have on your product side and how many you have on your reactant side, okay? So if we take a look at our equation here, how many do we have over here? What is the ratio? It's 2 to 1, 2 to 1, right? Okay, so we have a 2 to 1 ratio, right? So if I'm increasing my pressure, I want to go to the point where I'm taking up less room, right? So if I increase the total pressure by adding helium, then which way am I going to be shifting my reaction? It'll be to the products. So it'll be going in this direction, to the right, right? Because there's 2 molecules of this compared to 1 molecule, right? So the 2 molecules take up more room than the 1 molecule. Okay, so we're going to be shifting to make less, right? Okay, so then that would be to the right. So if I decrease my total pressure by transferring the reactant to a larger volume, then that does what? That's going to favor which one? To the, yes, to the left. Okay. Good, bad, ugly? Okay. Yeah, we're doing pretty good. I don't know what I'm going to do with myself when we finish. Maybe. People are going to start saying that I'm not teaching you guys if you guys keep going home early all the time. Yes, you're just quick learners. That's what it is. Okay, so this is called the Habenbash system. So this basically revolutionized the agricultural industries, production of ammonia. And so this basically uses a lot of the equilibrium that we've been talking about, right? So if you take a look at the system, so here, ammonia is basically made by the addition of nitrogen gas and hydrogen gas. And so it basically takes it from the air, which has an ample amount of, and then we get the production of nitrogen, right? I mean ammonia, sorry, not nitrogen. We get the production of nitrogen. It's in gaseous form initially, and then we make it into a liquid form. Another reaction by cooling. Okay, so okay, so there's our chemical equation, right? So here the gas enters, then the gas it travels down here, it's heated up, and then it's continuously heated, and then it travels up here, and by that heating, we're getting the reaction and the formation of ammonia gas, and we get the formation of, we'll have just more of our products. So then we go through a heat exchanger. And so by going through a heat exchanger, we get both of our products going through. This allows everything to kind of get cooled down, this heat exchanger, so it gets cooled down and cooled down. Then it comes over here. And as we cool down even further, what we end up doing is making liquid ammonia. The nitrogen and hydrogen gas goes back this way because they're still gases. They're always going to be gases, where ammonia can be cooled down to its liquid form. And so then this guy is removed from that system, right? So if we're constantly removing this, we're removing this by making this, which way are we driving the reaction? Are we going towards the reactor? So if we're removing, because basically we're removing this by removing it from the system. So when it goes into storage, it removes it from the system, right? So it's going to be driving, yes. Okay, so the reaction is going to be driven in this direction, right? Okay, because we're removing more and more of this. So basically, we constantly are removing the gas. We're constantly removing the gas, so it's pushing this reaction. Then what's going to happen is that it goes through. You have your stuff that's being recycled, and then you also have new stuff that's coming in, and you're making more and more and more, and then you're going to be driving this reaction. So you're going to get the production of more and more and more ammonia. Okay, beautiful system, right? You pretty much are making ammonia for free, right? You don't have to buy any products or anything like that. You're getting it straight from the atmosphere. Right? This is incredible. Like I said, it revolutionized the agricultural industry because, you know, at first they were like, hey, so where do we get fertilizer from? They get bones and all of that stuff. Here you just make it, you know, so. Okay, so let's start talking about, now that you guys understand the concept of equilibrium and you guys recognize, I'm going to ask you a couple of questions before we go on to our next topic. Okay, you guys ready? So, true or false? At equilibrium, you have equal amounts of products and reactants. Everybody, what do you guys think at NDC? Fireball. Maricel and Abel, what do you guys think?
Right now I'm thinking on it.
Okay. Maricel?
I feel like it's true because then wouldn't the equation have to be balanced so that they reach equilibrium? Or I could be wrong. I don't know.
So I'll repeat the question. So the question is, at equilibrium, you have equal amounts of products and reactants. True or false? The correct answer is false. Yeah, that was the same question. Same question. The correct answer is false. Okay, so now I'm going to ask you another question. True or false? At equilibrium, the rates are equal in the forward direction and in the opposite direction.
True.
What do you guys think? That's true. Yes. So it's the rates that are going to be the same. That's correct. Okay. So, true or false? Removing a product will drive the reaction towards the reactant. True or false? Okay. Well, let me write, I'll write down the question. It'll make it easier if I write it down so you guys can see it, right? You're like, because, so. Okay, true or false? Removing a product will drive the reaction towards the reactants.
False.
What do you think? The answer is false, right? So, just a reminder, because you missed the first part of the lecture. So if we have reactants, say A plus B, funny B, yields AB. So if we're removing this, it's going to try to get back to equilibrium. So you're basically changing your quotient, right? So we're taking this out. It's going to drive the reaction towards the product. So if I dump more of this in, it's going to do what? Drive it the other way. It's going to drive it towards the reactant. Okay. Does that make sense? Yes, if I add more of it, it's going to drive it that way. If you remove it, it's going to drive it this way. Okay, because you're going to make more product. Because remember, at equilibrium, so once it gets to equilibrium, it's stabilized, right? And so at that point, it's just going to be constantly making that amount. It's going to keep that same ratio or same, okay? So, but as soon as I disrupt it by removing one of them or another, then it's going to shift the reaction. It's going to change it, right? And then it's going to try to get back to equilibrium. So if you're removing this, it's going to go this way. If I'm removing the other side, it's going to go the other way. Or if I put in more of that side, it's going to drive it towards the product. If I put in more of this side, it's going to drive it towards the reactant. Okay. Okay. So I'll get back to this. So I'm going to come back to the 5% rule. But the first thing to do equilibrium calculation is that the very first thing that you're going to end up doing is kind of figuring out your constant. You need to find out your equilibrium constant. Make sure your equilibrium constant is given to you. In most cases, it is going to be given to you. You also are going to need to know the equation, right? Figure out the equation. You guys remember how to calc or write the equations? A refresher would be nice, but we'll go over it in a second here. Okay, so let's say, for instance, this is our chemical reaction. This is my equilibrium, right? So we have HA representing an acid. It's going to go to H plus and then our acid. So we know that this is what type of solution? If it's an acid, it's an aqueous solution. So that means that everything is going to be accounted for in our equation, right? So then our equilibrium constant is going to be what? KEQ is going to equal what? You don't have this slide. This is one that I made to talk about the 5% rule. And then I forgot, I cut off part of it. If you can see, solving for a block, and I deleted the other half. Don't know how I managed to. So how would I write the equilibrium equation normally? And the equilibrium equation, they're the same equation. Yeah. So the equilibrium equation is the same as the quotient. How would I write that? The quotient is just at any given point. The equilibrium is when it's at equilibrium, but the equation is the same. Okay, so how would I write it if this was my chemical equation for generic acid dissociation? You know, I realize sometimes I think I need those squeezy things. Stress balls, that's what they're stress balls. So how would I write it for this generic case? Okay. So H plus, concentration of H plus to the first power, so it's understood to the first power, times the concentration of A minus over HA. Okay, so that would be our equilibrium expression, right? This is how we write our equilibrium expression. So this is called the ICE table. ICE stands for initial, change, and equilibrium. So initially, we're starting off with a certain amount of acid, right? So this would be our value of, or our concentration at start, right? Initially, there's no products, right? At the very beginning, there's no products. So that would be our initial. So we put zeros here. Now, C represents change. So ICE, initial, change, and equilibrium. So change. So the change would be we're losing X, right? So if we're losing X, then that means that we're gaining X. Since we're talking about moles or molarity, then we can leave this in terms of X, right? Because this guy is a 1-to-1 ratio. So that means for every 1 mole that we lose of our acid, we're going to gain 1 hydrogen ion, and we're also going to gain 1 conjugate base. Okay. So, and that's because literally we have things that are together, right? And we're splitting in half. So we get 1 of this and 1 of that. Okay? So that's the reason why we're able to get 1 of 1, right? So for every X loss, we're going to gain, yes, in terms of our product. So then when we write at equilibrium, we're going to have the concentration initially minus X, because it represents both that initial minus the change. That's going to be our equilibrium, right? And then we're going to be gaining X. Okay. So then this equation is going to be, I'm just going to call this HA naught. HA naught. That's going to represent that. Not meaning the start. Minus X over X squared. Okay. And so normally you're given your equilibrium constant. So if we're given our equilibrium constant, then we can calculate and solve for X. And so that's basically how you would use the equilibrium expression to solve for your answer. Now, there is a rule called the 5% rule. Okay. So 5% rule basically means that if your value of this actual value is within 5% of what you believe it to be, then you don't take it into account, right? Or if it's less than 5% of this value, then you don't take it into account. Okay. So what you're going to do in this situation is that if we take the 5% rule into account, we basically will drop this minus and make it 0. Because we're assuming that if this is less than 5%, it's not going to affect this value too much. Okay. So to make our life easier, although this is an easy equation to solve, but a lot of times we get very complicated equations so that we have to end up using the quadratic formula to solve it. So, but to make our life easier, we're just going to make the assumption that this is 0, or it's so small that it's going to be close to 0. So then we'll just start off with the initial concentration is going to be, so make the assumption, let me circle this, is 0. So then you're starting with your equation looking like this now. H squared over, oops, HA naught equals K EQ. Yes. The 5% says that if this value is less than 5% of our initial, yeah, then we're okay. Right? So in other words, you're saying that this guy is going to be 95%, right? So then long as this is less than 5%, it's okay for us to make the assumption that this is 0. Sort of, yeah. Yeah, sort of like that. But this, it saves us time so that we don't always have to do a full calculation, right? Because if it's less than 5%, it's going to have very little effect on this value, right? But if it's greater than 5%, then yeah, then it's going to affect it. Then we're going to have to calculate it using the quadratic formula. So then we could just sit there and solve for x this way. So then we would just say K EQ times HA naught equals x squared. So then x is going to equal the square root of HA naught times EQ. Okay. You guys are with me so far? Yeah, HA naught. Yeah. Yeah, that's an A, sorry. No, this is the ice tables. Yeah, that's what ice tables are. Initial, change, and equilibrium, ice. Okay. You with me? Okay, so now let's see if we can do it, all right? We'll do a real problem. Okay, so use the following equation with an equilibrium constant Kc equals 9.30 times 10 to the minus 8 to calculate the concentration of hydrogen gas at equilibrium if 0.9450 moles of hydrogen sulfide gas is placed into a 3.00 liter container. And it's Kc, which means concentration, right? That's equilibrium constant for concentration. So we start off with an ice table. So we'll go ICE, I, C, E. Okay, so initially, what is my concentration of hydrogen sulfide gas? 0.15. But that's the number of moles, right? So this is placed in a, so if we want concentration, then we need to put it as mole, that's right, molar, that's right. So that's moles per liter, right? Okay. And then initially, how much do we have of this guy? We're starting off with what? Hydrogen. What are we starting off with? Put this in a container. All we've put in there is what? Hydrogen sulfide, right? So then how much am I starting off with? 0, right? Okay, so I'm starting off with 0. 0. Okay, so both of those are 0. Okay, so then the change would be, it would be negative 150? Are you sure? The change. Because the change is going to be based upon X. I mean, based upon the equilibrium constant. So our change is going to be minus X, right? Because you're removing that amount. So if I'm removing X at equilibrium, that means that the other side is doing what? You're gaining X, right? So this guy here, this first one, since it's a 1-to-1 ratio, right? This guy would be X, right? Since this guy is a 2-to-1 ratio, this guy would be also gaining. What was that? Half X?
Half X?
Half X, yes, that's right. 1/2 of X, right? So if this is X, this has to be half of it because it's a 1 for every 2 of these, we have 1 of these, right? So we have to have half of that amount. Yes. What was that? For the change, yeah, that's right. Yeah, because what you're losing, so your product, what you're losing from your reactant, you're gaining for your product. Does that make sense? Yeah. Yeah, so this, in this case, this guy is a 2-to-1, right? If it was also 1 here, right? Like we had earlier, then we would just use X. Does that make sense? Okay. So then our equilibrium is going to be 0.150 molar minus X. This guy is going to be X, and then this guy is going to be 1/2 X. Okay, so that's what it's going to be at equilibrium. So equilibrium is when you add it both, what you're starting off initially, and what you're going to change to. Okay, so then we have our equilibrium equation. So our equilibrium equation is Kc equals what? See if you guys can give me in terms of this. We'll put in the values that we have. Kc equals what? How would we write our equilibrium equation? Concentration of what over what? Parentheses H2 as its products over reactants. Okay. Squared, that's right. Times S2 over, that's right, the concentration of H2 S squared. Okay, so now we plug in our values here. So we have Kc equals,
Dr. Henry,
yes,
I have a question.
yes,
Or I didn't quite understand why was it like 0.150 instead of, or is
yeah,
not supposed to be 0.450?
because when we take the Kc, that means concentration. When we talk about concentration, concentration is in mole and is in molarity, right? Which is
Yeah.
moles over liters. So that would be our concentration. So if we went moles over liters, we have 0.45.
Oh, it's the conversion.
That's right, divided by
Oh, okay.
3 liters. Yeah. And so that's how we got that for our molarity.
Okay. Okay.
Good
Thank
question,
you.
though. Yes. EQ, because it means the same thing. It's equilibrium. EQ is just a very generic term. So, and Kc means we're talking specifically about concentration. Because if you look at this, these are all gases. We could have also said Kp for a pressure, right? And so we know that Kp relies only on the pressure, but we have to take RT if we want the equilibrium constant for concentration. Okay, you remember that? Where you have to divide it by the difference in how many of these guys you have, the number of moles that you have for this guy compared to this. So in this case, 3 to 2. So then that would mean you'd have 1 additional RT to multiply by. You don't remember that? It's like slide number 7 or something like that. So it's in that packet. Yeah. I can't remember which one exactly, but you'll see it. Yeah, but it is in that packet. Okay. So here, if we plug in our values, then we have x cubed 1/2 over 0.150 molar minus x. Yes. Because we have x here, and we have x here, right? So this is x squared, right? I got ahead of myself. Let me take a step back. I've got to remember, I see things that you guys don't right now. So this is x times 1/2 x. Because this here is just x squared, right? That's right, and I just combined it. Yep. So then you get Kc equals x cubed, 1/2 x cubed, all over 0.150 molar minus x. Now, this is where we apply the 5% rule, right? So we assume that this value here is going to be less than 5% of that value, of this value, right? So if it's less than 5%, we're just going to make this a 0, so we're not going to take into consideration. So then we get, oh, and I forgot to say this is squared, right? Sorry. That makes our life a whole lot easier, right? So then if we assume that only in the bottom, this x is less than 5%, so then we'll end up with Kc equals 1/2 x cubed divided by 0.150 molar squared. Okay, so then, do you mind if I go up here up top to finish this up? Okay. So then we can plug in our value for Kc. So we have 9.30 times 10 to the negative 8 is going to equal 1/2 x cubed and what is 1.5 squared. That's 0.00375. Okay, hold on. So 0.15 squared. Oh, yes. I don't know how I ended up with that. So. See, I was just testing. Oops, still got carried away. Okay, so then we bring this over. So we get 1/2 x cubed is going to be equal to 2 times 2 . So I get x cubed equals 4.185 times 10 to the minus 9. So then x is going to equal 0.00161 forward. So then we just check to make sure that falls within our 5% rule. Yes, it does. How do I check that? Because then I take this value here for X, and then I just divide it by my initial concentration. So it's actually, it's 1%. Are you with me? Okay. Oh, okay. Okay. Questions, concerns, cash, Kool-Aid? Okay. Did you get it? Sorry. Yeah, it's not getting it back now. It's gone. Okay. Okay. So then, now that I've shown you how to do this, I want you guys to work on this one, and then you guys take me through it. So calculate the equilibrium concentrations for all of the reactants and products if 0.500 moles of ICL is placed into a 5-liter flask with Kc equals 0.110. Walk me through the steps. What do I need to do? Ice table? Okay. So I C E. Okay. 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 So we have 0.100 for my molarity. Okay. It's going to start off at 0, 0. Okay. Let me move these over a little bit. Okay. So you said for the bottom, it's going to be negative X. Half X. That's right. Another half X. Okay. Kc equals okay. ICL squared. Okay. Okay. So I get 1/2 x, and that's all squared. Okay. Okay, so what is the assumption I'm going to make? 5% rule. Okay, so if I make the 5% rule, then I say that this is going to be equal to x squared over 0.100 molar squared. Okay, so I'm going to get Kc equals, that should be a fourth now. 1/4 x squared over, and you said 0.0 0 1 0. Okay. 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 Oh, square. Well, don't worry about the unit. So okay. Here you don't worry about the units because otherwise it. Okay. So then that means, what do we do next? We're plugging our value for Kc, right? So we get 0.110 equals 1/4 x squared divided by 0.0100 molar. Actually, we know molar squared. Okay, so then we get 0.0011 equals 1/4 x squared. So then that's 4. So then that will be 0.00044 equals x squared. So then x equals 66. Are you sure? 0.0663. Okay, so here we'll take a look at this number here, right? Now it's all perfect, it's all gravy if it's less than 5%. So we have 0.0663 divided by 0.1. So if I go, maybe I got the number down wrong. Is it 0.063663? 0.0663. Okay. Divided by 0.1. So that's 66%. So does that obey the so that's 66%. The 5% rule is 5%, 66% greater than 5%. Oh yeah, 66% is a lot greater than 5%, right? So that means that we have to solve this a different way. We can't do it the easy way. So we have to do it the shorter way, right? So then we're gonna have to take this value where we actually take this into account, okay? So let me show you how a way that you can do this. So now we have Kc, we have to take into account Kc is equal to 1/2 x squared divided by 0.100 minus x squared, right? So if I take the square root of both sides, including my Kc, so we take the square root of Kc of the whole thing. So then if I take the square root of 1.10 is what? Come on. So that is 0.332 equal to 1/2 x over 0.100 minus x. Okay. So then I multiply both sides by the numbers that are in the denominator. So then I'll get 0.332 times 0.10. That's right. And we solve for x. That's right. Equals 1/2 x.
So you can do either way, right? But the other way is more easier than the 5%.
That's right.
But you can do either way, right?
Yeah, this is one way. This is another way, right? There's also the quadratic formula. So then we have 0.0332 minus 0.332x equals 1/2 x. So then we solve for x. We'll bring this over to solve for x. So we get 0.0322 equals 0.83, right, a 2 x. So then we can get x is equal to 0.03 0, 3, 2, 2. Okay, so then X would be equal to 0.0387 molar. And this is kind of good because this also lets us know that if this number is greater than, if this number is greater than what we started off with, we know we've messed up somewhere, right? So this lets us know that pretty good, right? So then now we know what X is. And then if we wanted to calculate our concentrations for our products, then it's just half of that, right? Our answer is this. Yep. Because when we did it the first time and we assumed here, we got 0.0663. If you divide this by our initial concentration and divide 0.0663 by 0.1, what do you get? And multiply it by 100. Yes, because that's percentage, right? So that's greater than 5%. It's like 66%, which is significantly greater than 5%. So you actually have to calculate because that means that X value is a large part of it is being removed. Oh, after this, so then we have to start back over. So then I take the square root of both sides. That's what I did here. Then when I take the square root of both sides, this is what I ended up with. And then I was starting to solve for X. Here. And then I went here. Then I went here. Then I got my answer. I know it's written all over the place. Because this whole thing is squared, right? So then I take the square root of the entire thing. This is squared here. This is 1/2 X squared, right? This here is 0.11 minus X, it's squared. That's right. That's right. We take the square root of 9, 0.110. So the square root of that should be 0.3317, something like that. Good. Okay. So we'll stop here and we'll pick it back up on yeah, that day, Wednesday. I was gonna say Thursday, but can remember. Okay.